right, welcome to week 3. These are your fill-in notes, so make sure that you've printed a copy so that you can follow along. First slide, we see our objectives. We're going to be looking at the structure, the composition, and the isotopic information about an atom. And we're also going to determine the element's properties and patterns using the periodic table. So here we go. So we've learned already that an element is a pure substance. So think about what you've learned about pure substances. One of our definitions was that pure substances cannot be broken down into simpler substances by a chemical reaction. So an element is a pure substance. Each element is identified by a 1 or 2 letter symbol. We call that the chemical symbol. The first letter of this symbol is always capitalized, and if there's a second letter, it's always lowercase. So some examples of that would be S, capital S for sulfur, or a capital K for potassium. Or there are some that have 2-letter symbols, like iron is capital F, lowercase e. Sodium is capital N, lowercase a. So those are some examples of chemical symbols. Our elements are arranged in the periodic table based on patterns. So they're not just haphazardly put on this table, they're actually arranged in certain patterns based on properties. The position of an element in the periodic table tells us much about its chemical properties. And so we'll discover throughout the semester some really neat patterns in the periodic table, and just by knowing a little bit about the periodic table, you can know a whole lot about a lot of different chemicals and compounds. So I've put a link or a image of the periodic table in Blackboard. I would like to encourage you to stop now and download and print that copy of the periodic table. We're actually going to be writing some things on it and maybe shading some things in so that you can have a quick reference to your elements. So stop the video now and print off the periodic table that I've provided for you. So we're going to see a few things about the periodic table. First of all, the elements in the periodic table are divided into 3 groups, and that would be your metals, your nonmetals, and then we have something called metalloids. So we're going to take each one of these groups and talk about them just a little bit more. So the metals, they're located on the left side of the periodic table. They are good conductors of heat and electricity. So what do we mean by the word conductor? It's just the ability for heat or electricity to flow through that material. So metals make it good conductors. They tend to be shiny solids at room temperature. Except for mercury. Mercury is one exception. It's actually a liquid at room temperature. Our next category is nonmetals. Nonmetals are located on the right side of the periodic table. Nonmetals have a dull appearance. Instead of being shiny like metals, they're actually dull. They do not reflect light very well. They are usually poor conductors of heat and electricity. And nonmetals can be solids, liquids, or gases at room temperature. So down below there's some examples of nonmetals that are solids. Sulfur and carbon are nonmetals and they're solid at room temperature. Bromine, which is something we know a lot about in South Arkansas, it's actually liquid at room temperature. And then we have some gases, nitrogen and oxygen. Gases at room temperature, so they come in all varieties. And then we have a very important group called metalloids. So these are located on what's called the stair step. I'll show you what that looks like. The stair step that starts at boron and angles down toward astatine. So just a few mentions about properties. Metalloids have properties of both metals and nonmetals. So they're somewhere in between metals and nonmetals. And because of these properties, metalloids are very useful in a lot of our electronic technology world. This stair step, the reason it's so important is it is actually the dividing line between metals and nonmetals. And so when we go back to our periodic table in just a moment, we'll see that that's how we know if something is a metal or a nonmetal based on where it's located in reference to the metalloids. So there are 6 common agreed upon metalloids, and they're listed here, and we'll mark those on our periodic table in just a moment. I say commonly agreed upon because not everybody in the science world agrees on these 6. They think there's more than 6, and so we'll just keep it at 6. So I would like for you to go back to your periodic table. Hopefully you've made a copy of that. And the first thing we want to mark are our metalloids. So if you happen to have a highlighter or a colored pencil or something, if you can just mark these. So we have boron, and then we have silicon, and then we have germanium and arsenic. We have antimony, and we have tellurium. So as you see, by marking these, you can see kind of the stair-step look of the metalloids. And as I said, this is the dividing line then between metals and nonmetals. And so also we want to mark these different, trying to get a different color, sorry. Here we go. So metals, it said we're on the left-hand side of the periodic table, so everything to the left are metals. So I'll just make a big, these are all metals. So you can see the majority of the table are metals. All of this would also be, these are also metals. And then under the stair step, so all of these, you don't have to color all of these, but just so you know, all of these are metals. I'll just highlight these in green. These are considered metals. So by far, the majority of the table are metals. And then on the right-hand side of the stair step, we have our nonmetals. So we have this group. So very few, as you can see, are actually nonmetals. So that's kind of the breakdown of the periodic table in terms of the 3 groups. All right, let's see what else we have. So just taking a look at why these are important to us as humans. Elements are very important. There are 4 elements that comprise 96% of the mass of the human body. So these, particularly these 4, but more than just these 4. So we have oxygen, and that symbol is a capital O. We have hydrogen, that symbol is a capital H. We have carbon, that symbol is a capital C, and we have nitrogen. That's a capital N. So these 4 make up 96% of the human body. So carbon, hydrogen, and oxygen are found in the 4 types of biological molecules that you studied in biology: proteins, carbohydrates, lipids, and nucleic acids. So those are very important to us. Also in proteins and nucleic acids, we have nitrogen, which is the fourth element mentioned above. So we'll speak more about these biological elements and molecules as we move through the year. Here are some, not only the four elements that we just mentioned, but there's also some major minerals that are important to us that are also found on the periodic table. Here's potassium and sodium and chlorine. That says they're all present in body fluids. We have magnesium and sulfur found in muscles. We have calcium and phosphorus found in our teeth and bones. And then there's also trace elements which are important, and they're listed here: arsenic, boron, and so on. So all of these are very important in our diet, and so that's why we have to eat the right kinds of foods or take supplements if we're not getting the vitamins and minerals that we need. All right, let's move on to something called compounds. So we've studied compounds before. We know that compounds are also pure substances. They're formed by chemically combining two or more elements together. And so when we have a compound, we show that by writing something called a chemical formula. So a chemical formula consists of the element symbols. So in the formula, we show the different symbols to see what elements are involved. And they also contain subscripts. And so subscripts show the ratio of atoms in the compound. So two examples here, we have water, which is common to all of us, H2O. The subscript 2 goes with the element in front of it. So there are two hydrogens and one oxygen. Over here we have propane. You see it's C3H8, meaning 3 carbon and 8 hydrogen. All right, let's talk a little about the structure of the atom. We know that all matter is composed of the same basic building blocks, and those are called atoms. And atoms are composed of 3 subatomic particles, which are listed in this table. And so the table shows us the charge and the mass in grams and the mass in AMU. So the subatomic particles are protons, and they have a charge of +1, and so typically we write the abbreviation for proton is a lowercase p with a little plus superscript. And next we have neutrons, and neutrons have no charge, they're neutral, so typically it's a lowercase n with a 0, meaning a no charge. And then we have electrons. Electrons have a negative charge, so their symbol is a lowercase e with a negative sign. And you can see a little bit about the mass of these subatomic particles. Notice that the mass of a proton is 1, and the mass of a neutron is 1, whereas the mass of an electron is so very small that it is negligible, doesn't really matter. So the mass of the atom is made up of protons and neutrons. So the entire mass of the atom is found in the nucleus of the atom, which contains the protons and the neutrons. So quickly we'll just review the structure of the atom. We know we have the nucleus. It's located in the center of the atom, and that's where the protons and the neutrons are. It's very dense, and as I said before, it contains most of the atom's mass. And then surrounding the nucleus, we have what's called an electron cloud. This is where the electrons are located. They make up most of the volume of the atom, and it's mostly empty space. When we think about charges, protons have a positive charge, electrons have a negative charge, and then these neutrons have a neutral charge. Well, we need to know something about this attraction and repulsion of charges. So opposite charges attract each other. So think about a magnet. If you have a magnet with a north and south pole, That's a positive and negative pole, and you know they attract each other. But as soon as you turn around the magnet and you have two north poles next to each other, they repel. So like charges repel each other. Protons and electrons attract each other because protons are positive and electrons are negative. But if you have two electrons, they repel each other. And so this diagram is showing that. All right, if we take a look at the periodic table, and if you find the element lithium, it is element number 3. It has an atomic number of 3. The atomic number is 3. And that atomic number is given a symbol. A capital Z stands for atomic number. And it turns out that the atomic number is also the number of protons. Atomic number equals the number of protons. So every atom of a given element has the same number of protons. So all atoms of lithium all have 3 protons. All atoms of carbon all have 6 protons. Whereas different elements have different atomic numbers and therefore different numbers of protons. When we talk about an element on the periodic table, we tend to say that they have a neutral charge, a neutral nucleus, which means they have no net overall charge. So in this case, the Z, or the atomic number, is equal to the number of protons and the number of electrons, because it's protons and electrons that determine the charge of the atom. So let's say, for example, we have lithium. We see that it has 3 protons, and so we know protons have a positive charge, so we write a +3. And then if we want to know the overall charge, we have to add the protons and the electrons. And so a neutral atom of lithium would have 3 electrons. When you add that together, you get a charge of 0. So the charge is determined by both protons and electrons. All right, let's talk a moment about something called isotopes. Isotopes are atoms of the same element that have a different number of neutrons. Atoms of the same element with a different number of neutrons. And because there are a different number of neutrons, each isotope has a different mass number. And mass number is given the symbol of A. So atomic number is Z, and mass number is A. And so we see in our example here, we have 2 isotopes of chlorine. Cl is chlorine. The first isotope of chlorine has a mass number of 35 and an atomic number of 17. If you find chlorine on your periodic table, you see that it has an atomic number of 17. In order to find the neutrons, we have to take the mass number minus the atomic number. And so the number of neutrons in this case would be 18. Remember, an isotope is an atom of the same element that has a different number of neutrons. So when we look at our second example here, we still have chlorine with an atomic number of 17, but this time it has a mass number of 37. So how many protons does it have? 17. How many electrons? 17. But the number of neutrons would be the mass number minus the atomic number. This one has a 20 for the number of neutrons. So these two are isotopes of each other. So an isotope. On the periodic table, we not only do we see the symbol and the atomic number, but directly under that is something called the atomic weight, or I like to refer to it as the average atomic mass. The average atomic mass. This number is a weighted average of all of the naturally occurring isotopes of that particular element. And so that explains why their decimals, the atomic weight on the periodic table, mostly are in the form of decimals. And so we'll look at how to find a weighted average. This is different than just a normal average, a weighted average. And so when we look at our next slide here, how to determine that atomic weight or the average atomic mass. And so our question is, what is the atomic weight of chlorine? And so the first thing you want to do is take a look at all the naturally occurring isotopes. And so generally these will be given to you in the form of a table or in a sentence. Chlorine has 2 naturally occurring isotopes, as we saw earlier. We have chlorine-35. This is a hyphen notation showing the mass number of each of the isotopes. Chlorine-35 and chlorine-37. In the middle we see that they have mass numbers listed here, and they also have something called the isotopic abundance, or the percent abundance. And so if we went on a field trip to find some isotopes of chlorine, 75.78% of the time we would find chlorine-35, and 24.22% of the time we would find chlorine-37. So this is how abundant these isotopes are in nature. All right, so once we know the isotope mass and the percent abundance, then we can figure out what is the average atomic mass or the atomic weight of the element. So step 2, it says multiply the isotopic abundance. Notice that it's changed to a decimal. That's very important. Multiply that percentage by the mass of each of the isotopes, and then you add up the products. This sum is the atomic weight, or the average atomic mass. So let's walk through what they did. So we have our first isotope, chlorine-35, and it has a mass number of 34.97. We're going to multiply that by the percent abundance changed to a decimal. So when you want to change a percentage to a decimal, you simply drop the percent sign and move the decimal 2 places to the left. So let's make a note of that. To change a percent to a decimal, you move the decimal 2 places to the left. So maybe you want to know why 2 places. Well, when you think about percentages, if you have the whole sample, that would be 100%. And so percentages are typically out of 100%. And one way to remember the 2 places is 100 has 2 zeros. And so when we change the percentage to a decimal, we're basically dividing by 100, which means we move the decimal place 2 places to the left. So then we do the same for our other isotope. Chlorine-37 has a mass of 36.97, and it has a percent abundance of 0.2422. And these are the answers that we got when we multiplied, and now we're simply going to add these together. So a weighted average is different than a normal average. We're just going to add these together and we get our average atomic mass, which is 35.45. Remember, when you're adding numbers, you go with the least amount of decimal places, and that would be 2 decimal places, which is what we see here. So first you want to multiply the mass number times the percent, change to a decimal, and then you want to add the 2 numbers together. If you were putting this in the calculator, this would be how I would enter it in the calculator, just all one problem. So I would use parentheses on your calculator. So you open a parentheses and you would type 34.97 times 0.7578, close the parentheses, plus, open another parentheses, 36.97 times 0.2422, close the parentheses, and hit select enter. And that way you're least likely to make mistakes if you put it all in at one time. Don't forget to round to the correct number of decimal places. All right, that concludes our notes for this portion, week 3. Now it's time for you to practice.